discuss about different geoid determination methods. So RCR, remove compute yesterday. I think you're already familiar with the RCR technique, but how they apply this to for geoid determination. So they have Stokes integral as usual, and the gravity data inside the Stokes formula will be reduced for two things: delta G RTM, score residual train model minus gravity anomaly up to degree L is from the EGM. Remove, and thereafter they will restore the effect of RTM and NL from a gravity model. So as you see, there is no modification, no kernel modification is here, and they assume that the long wavelength structure of the gravity field, which is normally taken from the satellite gravity models, these ones, are already known. Of course, the higher this value of this, the degree of the spherical harmonic of the gravity is, the contribution of the Stokes integral will be less, because this part of the signal, this part, is strong. So if this degree is too low, then the role of the terrestrial data will be higher. And when this L is too high, the role of this N is higher. Now RTM is a residual train model. Let me explain this a little bit. It is similar to the topographic effect. So if you have your computation point somewhere here, and you are at this point, you have the effect of this shell. It's like a train effect. Then you can compute the effect of this roughness. So they will remove that high frequencies as well. So you see the high frequencies are removed from the RCR data in addition to low frequencies. Long and low frequencies are removed from the data, and later they are restored. So the quality, my concern about this method is that, for example, let us see the general formula. I have a quantity A, and in this case, the error of A is sigma 1. Now, I say A minus B plus B. What will be the error of this one? If we assume that there are only random errors here, the error will be sigma R plus 2 times variance of B. This means that the error, the random error of this quantity, which is remove and restore, is contribute to the result, error of the result. So when you assume that this gravity is known, the gravity or low frequencies are known, it means that they are absolutely correct. So if this is so, you disregard the errors of this model. I would say that if I change this long wavelength, the structure of the geoid, the result of the geoid model that I compute is strongly dependent on the choice of this long wavelength. So if I change this long wavelength, the result of the geoid will change. And the quality of these long wavelengths are not actually considered in the method. So that's a problem. We do not know how much they can. Normally, the simple things that they do is that they compute. They have GPS leveling data or GNSS leveling data. It doesn't matter which term I use to say. What is that? I have this ellipsoid and I have the geoid, and this is ellipsoid, and this is the GNSS leveling point. And we know that this height is geodetic height, and we show it by h, and this one is orthometric height, we show it by larger, and this distance is the geoid height, which we compute simply from this formula. So the n is equal to h minus h. So how do they determine the best line wavelength? The best values for that, the maximum degree of that. The simple way is to do the trial and error. They will select a gravity model and perform this remove restore method. Perform this remove restore. So I come to the geoid at the end. They come here. They compute this geoid and compare it to this geoid, which comes from GNSS leveling. They compare to see if the result is close to that or not. If it is close, then that's fine. They will different gravity models to perform this remove restore to get the closest value to the GNSS leveling data. And also the RT. What is happening? Well, if I have gravity anomaly here, and if I remove the high frequencies, RT, then I remain a medium frequency and delta G from low frequencies. If you look at this signal is much stronger. When L is higher, then it will be stronger. Therefore, your geoid will be closer to the geoid that the gravity model gives to you. And also the error based on, show that the error based on propagation law is also there. Another issue is that they do not modify the integral. They believe that by removing the long wavelength structure of the gravity, and due to the orthogonality of this Stokes kernel function, get base functions to this delta G, they can reduce the effect of far zone data. But it is not enough, actually. Professor Schoberg has written a paper in 2005 and discussed about the accuracy of RCR method. So that RCR method, of course, theoretically it is correct, but there are practically issues. So another issue is that these data, which are here inside the integrator, they should be continued downward. So what is happening? Then they will remove. Let me write a flowchart, simple flowchart. They will, if they have delta G, they will perform remove delta G RTM, high frequencies and low frequencies of that. What you get is medium frequency. Later, let me go up the gain. Later, they perform downward continuation of this medium frequency. After that, Stokes integration. And after that, restore the effect of remove RTM and the global variety model. Then you take on to Geoid. And how do you do these things? The first step to the best choice of the best gravity model is done by trial and error and comparing with the GPS leveling data. That's very standard in Geoid determination. But the result is it depends on this line wavelength structures. Because the short wavelengths are not coming from the gravity, are coming from the topographic data. If you have precise topographic data, then you will be at the safe side to remove it from this. But this N from the long wavelength will be different from one model to another, and they find the best model from this model by comparing the GNSS leveling. And by this principle, they come to the Geoid. And note that it is we do not modify the integral, but I have here that recently they have applied Wong and Gore modification for that. Yeah. And they try to use a fast Fourier transform for speeding up the computations. So that was some technicality, but theoretically everything is more or less the same method. Just the RCR method.